Hi, in this video I would like to introduce the concept of formal charge, which is used to determine if a Lewis structure is minimized in energy. So we do this to determine if there's some kind of uneven charge distribution in a Lewis dot structure, and if so, that might mean that the molecule is not drawn correctly or that there's some kind of charge imbalance. So in most cases, this is used to check whether you've drawn a Lewis dot structure correctly. Formal charge is calculated by taking the number of valence electrons in the free atom, so for example 4 in the case of carbon, minus 1/2 of the electrons that are bonded to something else. So say if the carbon has 2 bonds, we would say it have 1/2 of the 2 bonds. Each bond has 4 electrons, so 1/2 times 4 minus the number of non-bonding electrons. So this is a kind of a poor example. Let's look at the example here of the ozone molecule down here. So we see that if we write out the Lewis dot structure of the ozone molecule, O3, that's an allotrope of oxygen, and that has a resonance structure. And so we can either have the double bond on this side of the oxygen or on that side of the oxygen. But let's calculate the formal charge for all of these oxygen atoms in the ozone molecule. If we do it here for the left-hand one, we see so oxygen has 6 valence electrons, and then it has 4 bonded electrons in these 2 double bonds right here. So and we multiply that times 1/2, and then it has 2 lone electron pairs, so 4 electrons that are not bonded. So those are right here, and then we indicate that by subtracting 4 from this relationship, and we end up with the formal charge of this oxygen right here is 0. Likewise, the one in the center is calculated in the same fashion. We have 6 valence electrons for the free atom right here, the valence electrons in the free atom, minus 1/2 times 6. In this case, there are 6 electrons bonded to something else in the 3 bonds that are surrounding this oxygen atom, and it has 2 lone electron pairs, so the formal charge for this oxygen atom is plus 1. And then for the oxygen atom on the right, it has, again, 6 valence electrons, and only 2 electrons bonded to something else, to the other adjacent oxygen atom. So multiply that number times 1/2, and then we subtract the 6 non-bonded electron pairs, and we end up with a formal charge of minus 1. So there's a little bit of a charge imbalance in this molecule, and this is perfectly fine, but you notice right here the formal charges add up to 0. This is a neutral molecule, so therefore the formal charges add up to 0. For a neutral molecule, they add up to 0. For an ion, the formal charge must add up to the overall charge of the ion. Let's do an example with nitrate, which we saw in class, and do another example of the formal charge calculation for nitrate. So for nitrate, NO3-, that's the nitrate ion, and we said that it has a resonance structure, and so let's just draw one of the possible solutions right here. So we have nitrogen, and this has a negative charge right here, and then there's one of these oxygens will have a double bond, and the remaining oxygens will have a single bond to the nitrogen. And overall, this will have a negative charge, and let's see why. So let's calculate the formal charge of this oxygen right here. So you need to calculate the formal charge for all the atoms that are equivalent. So in this case, we notice that these 2 oxygens right here are structurally the same. So this one right here and that one right here. So we can calculate the same value for both of these. So the formal charge for these is, so we can calculate that. So this is for the single bond oxygen bonded bound to the nitrogen, and this would then be 6 because oxygen has 6 valence electrons minus 1/2 times 2 bonded electrons. So that's the 2 electrons in the bond to the nitrogen, and minus, we want to then subtract 6 lone electron pairs that are not bonded to anything. So minus 6. And so if we calculate that, we end up with minus 1. And for this oxygen right here, for this oxygen with a double bond to the nitrogen, the formal charge for that one is, and we start off with 6 minus 1/2 times the bonding electrons, so those would be 4 in this case, because there's a double bond. And in this case, the oxygen only has 2 lone electron pairs, so that would be minus 4. And so that would equal then 6 minus 2 minus 4 equals 0. And then if we calculate the formal charge for this nitrogen right here, nitrogen has 5 valence electrons, and minus 1/2 times 8 electrons that are bonded to something else. So there's 4 bonds attached to this nitrogen, so 8 electrons. And nitrogen in this case has no lone pair electrons, so we can say this is minus 0. And this would then add 5 minus 4 equals plus 1. So there's a charge imbalance in there, but that's fine. And we need to always make sure we minimize these formal charges. They don't necessarily have to be 0, but they have to be minimized. In this case, they are minimized. In the next example, we'll see how to optimize the formal charges. So in this case, we see that we have 2 of these oxygens with a minus 1 charge, and with a minus 1 formal charge, 1 with a 0 charge, and then plus 1. So this as a total adds up to minus 1, because we've got 2 of these oxygens that have a minus 1 formal charge, and then plus 1 for the nitrogen. The total adds up to minus 1. We can also use the concept of formal charge to optimize a structure when we are drawing it. So if we come up with 2 plausible solutions, the one with the minimized formal charge is the valid one. If we come up with 2 or more solutions, but they all have the same formal charge, then we have a resonance structure. In the case of the nitrate ion, I can draw this ion right here with a double bond over here or over here. The formal charges will be the same. Likewise, in the case of the ozone molecule here in the first slide, if I draw the double bond over here and leave this oxygen with a single bond, the formal charge will be the same. However, if we do the example indicated here, if we want to draw the Lewis dot structure of formaldehyde, we can use formal charges to determine which of these skeletal arrangements of atoms is the best choice for a Lewis structure of this molecule. So we can arrange this structure this way or this way, and if we do the Lewis dot structures, we can find out and calculate the formal charge. We can find out what the correct arrangement is. So if we do that and calculate the formal charge, we can see that for this arrangement over here, this carbon right here would have a formal charge of 4. Formal charge of this carbon with a double bond to the oxygen would have a formal charge of 4. Carbon has 4 valence electrons, minus 1/2 times 6 electrons that are bonded to something else, minus 2 lone electron pairs, and that would equal minus 1. And if we do this for this oxygen right here, the same thing. So we start off with the formal charge of the oxygen with the double bond to the carbon, and we end up with 6 for valence electrons for the oxygen, minus 1/2 times 6 electrons that are bonded to something else, minus 2 lone pair electrons, and that equals +1. Now, if we do this on this structure over here, we see that carbon in this case would be again 4. The 4 mole charge would be, let's write this all out properly, of the carbon to the oxygen. 4 mole charge would be 4 minus 1/2 times 8, because there's 8 bonded electrons around this carbon, and then there's no lone pair, so 0, and so that would equal 0. So 4 minus 1/2 times 8 is 0, and then for this oxygen up here, we also end up with 0. We start off with 6, so 4 mole charge of the oxygen. Let's write this a little neater. Equals 6 minus 1/2 times the 4 bonding electrons right there, minus 4 non-bonding electrons, and that also equals 0. So you notice right here, in this arrangement on the right, the 4 mole charge for both of these is 0, for carbon and oxygen is 0. For, in this case right here, it is minus 1, and plus 1. So the arrangement on the right, where the 4 mole charges are minimized, is the correct one. The one on the left would not be plausible because the 4 mole charges are not minimized. Note, hydrogen always has the same 4 mole charge of 0. You can prove that to yourself. It has 2 valence electrons minus 1/2 times 2. So that would be, it has 1 valence electron, and minus 1/2 times 2 electrons bonded is always 0 because it's always the terminal atom. So this one is always 0. Worth checking that, but if in doubt, you can check that yourself. And that's it. So let's see if you can do this next problem. And pause for a minute if you wish. So in this case, you want to determine the 4 mole charge on the oxygen in the carbon-oxygen single bond of the carbonate ion. So see if you can do that. Take a minute and pause this video. And I hope you did well. Thank you for watching.